All right, today we'll be working on the applications of second derivative. In previous class, we worked on application of first derivative, but today we are working on the application of second derivative. So let's quickly read these three applications, and then we are going to solve the examples based on that. Following are some important applications of second derivative of a function. The first one is second derivative help us to determine the concavity. When we say concavity, when we talk about concavity, it is the interval on which the function is concave up or concave down. Now, when I say the function is concave up, meaning of that is the graph of the function is either like that. So if you look at it, it's concave up, the cup shaped is up, or maybe if it is like this, then also that is concave up. That's also concave up. If you see the shape of the graph like this or this one, meaning of that is the graph is concave up. And the place where the graph is concave up, or the interval on which the graph is concave up, your second derivative of the function will be positive. If second derivative is positive, the function is concave up. Similarly, we can find the interval on which the graph of the function is concave down. When we say concave down, you'll have a graph shape like that on the interval, or graph shape like this. In both cases, you can see that it is concave downward. So in this case, your second derivative of the function is negative. Second derivative helps us to determine the inflection points. Inflection points, these are the points, okay, where the second derivative of the function is 0 or undefined. That is, we are going to find the inflection point using second derivative, or second derivative will help us to determine the inflection points. These are the points on the graph where the second derivative of the function, you can see here, the second derivative of the function is 0 or undefined. So if you are asked to find the inflection point, you have to look for the place where the second derivative, okay, second derivative of the function is 0, or the second derivative of the function is undefined. So meaning of that is the place on the graph where the second derivative is 0 or the second derivative is undefined, we call that point the inflection point. And also sometimes we say that inflection points are the points at which the concavity of the graph of the function changes. That is, from concave up, it will go to concave down, or from concave down, it will go to concave up. So those points where the concavity changes, that is the inflection point. And the last one, what we have to do is, or what we can do is, by using the second derivative, we'll be able to compute the maximum and minimum value of the function. What we know from the previous lecture is the maximum and minimum value occurs at critical points. So maximum or minimum values occurs at critical points. Critical points, that is what we know from the previous lecture. So when I say critical points, these are the points where the first derivative is 0 or first derivative is undefined. Those are the critical points. That is what we know from the previous lecture. So maximum or minimum value occurs at critical points. So in order to find the critical point, you have to set the first derivative to 0 or first derivative undefined. And once we have that, we have to find the second derivative. If second derivative, okay, if second derivative at critical point is positive, please note this one. If second derivative f double prime at critical point is positive, then function is minimum. Function is minimum at that point. Minimum at that point. So you can see we are using the second derivative to verify whether you have a maximum or minimum at the critical point. So if the second derivative at critical point is positive, the function is minimum. So you can clearly tell that if second derivative at critical point is negative or less than 0, the function is maximum now. The function is maximum at that point. Maximum at that point. So very clearly, we are using the second derivative to determine the maximum or minimum value of the function. So these are the three important applications of the second derivative that we are going to explore in this lecture. Example, determine the inflection points on the graph of the function. So in this example, we are looking for the inflection points on the graph of this function. When we say inflection points, these are the points where the second derivative of the function is 0, or the second derivative of the function is undefined. That means first we have to find the second derivative, and we have to check where it is 0 and where it is undefined. So let's begin with the function here. Here my function is f of x equal to x cubed divided by x squared minus 1. Now we need to get the first derivative, then only we'll be able to go to the second derivative. So let's find the first derivative of this function. In order to find the first derivative of the function, it is in the form of a quotient. So we are going to use the quotient rule. Quotient rule says denominator, which is x squared minus 1, multiplied with the derivative of the numerator, that is derivative of x cubed, minus numerator times the derivative of denominator, which is x squared minus 1, all divided by the square of the denominator. So this is equal to, in the numerator I have x squared minus 1, multiplied to derivative of x cubed by using power rule. We bring that 3 down and we reduce the power by 1, so that will be 3x squared. So derivative of x cubed is 3x squared minus x cubed multiplied to derivative of 1 is 0, and derivative of x squared by using the power rule is we bring the 2 down and reduce the power by 1, so that will be 2x. Divided by, in the denominator we have x squared minus 1 quantity squared. This implies f prime x, or the first derivative, is equal to, we can distribute this 3x squared over here. So if you do that, 3x squared multiplied to x squared is 3x to the 4. 3x to the 4 minus 3x squared multiplied to 1 is 3x squared. Then minus again, this minus x cubed multiplied to 2x is 2x to the 4. 2x to the 4 over x squared minus 1 quantity squared. So we get the first derivative here. So the first derivative is equal to, okay, so if you look at the numerator, we have 3x to the 4 minus 2x to the 4, that is 1x to the 4. 1x to the 4. Then minus, we have a 3x squared. 3x squared. And the denominator is x squared minus 1 quantity squared. X squared minus 1 quantity squared. So this is my first derivative. In order to get the inflection points, I need the second derivative. So I need to differentiate this one more time. Okay, this is what we get for the first derivative. So I mean to write this. We have the first derivative equal to this. Now I'm going to differentiate this again and get the second derivative. Again, this is in the form of a quotient, so we have to use the quotient rule. So second derivative f double prime x is equal to, because it is in the form of quotient, we use the quotient rule. Quotient rule says denominator, which is x squared minus 1 quantity squared, multiplied with the derivative of numerator. Numerator is x to the 4 minus 3x squared. Then minus numerator. Numerator is x to the 4 minus 3x squared times the derivative of denominator. Derivative with respect to x of denominator is x squared minus 1, quantity squared, all divided by the square of the denominator. X squared minus 1, quantity squared is there, and when you square it again, it should be raised to power 4. Okay, now we are going to simplify this and make it a little beautiful. Second derivative is equal to, in the numerator I have x squared minus 1, quantity squared, multiply with the derivative of this. Derivative of x to the 4 by using the power rule. 4 will come in front, and we reduce the power by 1. So that will be 4x cubed. 4x cubed minus, over here 3 is a constant multiple, it will stay there, and we find the derivative of x squared using the power rule. So 2 will come down, multiply with 3, that will be 6, and here we reduce the power by 1, so that will be 6x. 6x. Then minus, we have x to the 4 minus 3x squared. And then in order to find the derivative of this one, we have an inside function x squared minus 1, and the outside function is a power function, is squared. So what we are going to do is we are going to use the chain rule. Chain rule says the derivative of outside function first. So for the outside function, we bring the power down and reduce the power by 1. Bring the power down, reduce the power by 1. So 2 minus 1 will be 1. And then multiply by the derivative of inside function. Your inside function is x squared minus 1. Derivative of 1 is 0. Derivative of x squared by using the power rule. We bring the 2 down and reduce the power by 1. So that will be 2x. 2x. In the denominator, we have x squared minus 1 raised to 4. We are going to leave it like that. Now, if you look at the numerator carefully, there is one factor that is common. Like this one, we have x squared minus 1 quantity squared on the first term. And on the second term, here is x squared minus 1. So I can factor this out. So here I have 2 of them. When I factor out, 1 of them will remain. Here, when I factor this out, this will completely come out. So what we'll get is this. Let me write here, second derivative is equal to, I'm factoring out that x squared minus 1. After factoring this out, there are 2 of them. 1 of them will still remain there. So x squared minus 1 is still there. The other quantity that is there is 4x cubed minus 6x. And then minus, now in the second term, you have to be very careful and you have to look at it carefully. This is already factored out. Here we are left with 2 times 2, 4x multiplied to that. So 4x multiplied to x to the 4 minus 3x squared. And then in the denominator, look at the denominator carefully. We have x squared minus 1 raised to 4, which can be written as x squared minus 1 multiplied to x squared minus 1 raised to 3. 3 and 1, that is 4. The reason is, by writing like that, we'll be able to cancel this factor which is outside. X squared minus 1, x squared minus 1. We can say goodbye to those 2. Next step, second derivative. Let's see. The second derivative is equal to, now in the numerator, we are going to multiply these 2. So x squared multiplied to 4x cubed will be 4x to the 5. Okay, when you multiply, it will be 4x to the 5. And then x squared multiplied to negative 6x will be negative 6x cubed. Negative x squared, and then here is a 6x. So if you multiply, it will be negative 6x cubed. Negative 6x cubed. And when you multiply by negative 1, it will be negative 4x cubed. Negative 4x cubed. and then -1 multiplied to -6x, negative and negative, positive 6x, positive 6x. Then minus, this minus here, if I multiply by that, it will be 4x to the 5, 4x to the 5, minus and minus, if I multiply this, positive 4 times 3, 12x cubed, 12x cubed, divided by, in the denominator we have x squared minus 1 quantity cubed. So we can write the second derivative is equal to, in the numerator you can see this 4x to the 5 gets cancelled, and then when you look at it carefully, look at the x cubed. Here we have 12x cubed, and here we have minus 6x cubed. 12 minus 6 is 6, and also we have minus 4x cubed. So it will be 2x cubed. Or you can think like this, -6 and -4. That's -10. -10 and positive 12 is positive 2. So it will be 2x cubed. 2x to the third. And after that, when x to the third are all taken care of, we have plus 6x there. Plus 6x, 2x cubed plus 6x over, in the denominator we have x squared minus 1 quantity cubed. That is my second derivative. Okay, we got the second derivative as 2x cubed plus 6x over x squared minus 1 quantity cubed. Now, if we look at the problem, we are asked to find the inflection points. These are the points where the second derivative is 0 or the second derivative is undefined on the graph of the function. Now, our function is x cubed over x squared minus 1. And the domain of this function is all x except x is positive or -1. Positive or -1 is not in the domain of this function, because if you plug in x equal to +1 or -1 and square it, +1 or -1 squared is 1, 1 minus 1 will be 0, and something over 0, that will be undefined. So this function will be undefined at plus or minus 1. That means the domain of this function is everything from -infinity up to infinity except -1 and +1. -1 and +1 are not there in the domain of the function. That is something we really need to remember when you want to find the inflection points. So when we say these are not in the domain, these are not the values that are on the graph also. We don't have any point corresponds to x equal to -1 and x equal to +1 on the graph of this function. So if we are getting -1 and +1 as the critical points, these are not the critical points. That is something to note. Now, if we look at the second derivative, this is my second derivative. In order to find the inflection points. So in order to find the inflection points, we have to check where the second derivative is 0. Now, we can say this, second derivative is 0. Okay, second derivative is 0 when, see, second derivative is in the form of a fraction. A fraction is 0 when the numerator is 0. That is when 2x cubed plus 6x is equal to 0. Then what we get is, if we try to solve this equation, let's see what we get. 2x is a common factor. You get x squared plus 3 equal to 0. So meaning of that is 2x equal to 0 or x squared plus 3 equal to 0. When the product of two factors is equal to 0, then we can say either the first one is 0 or the second one is 0. So from the first, x equal to 0. From the first, x equal to 0, or from the second, if you try to solve this one, you'll move 3 on the other side. It will be -3, and you'll take the square root. And the square root of -3 will be 3i. It's not real. So this is not in the domain. So the value, which is x equal to plus or minus 3i, this is not in the domain. Not in the domain. Because domain is a real number from negative infinity to positive infinity except plus or minus 1. So here we just got one value, x equal to 0. That is one of the candidate for the inflection point. That is when the second derivative is 0. Now we still have the second condition. When is the second derivative undefined? Let's check that. Also, the second derivative is undefined. Second derivative is undefined when, okay, second derivative is in the form of a fraction. A fraction will be undefined when the denominator is 0. That is when x squared minus 1 quantity cubed is equal to 0. Now, if you take cube root on both sides, you get x squared minus 1 equal to 0. If you add 1 on both sides, x squared equal to 1. And then when you take the square root on both sides, you will get x equal to plus or minus 1. But what we know is the domain of the function is from negative infinity to infinity except plus or minus 1. So these values are not in the domain again. So these values, they are not in the domain. Not in the domain. Those two values are not in the domain. That means the only candidate for the inflection point is x equal to 0. So what is the inflection point? That is the point on the graph satisfying this condition. So if you want to find the point in the graph, point is written in the form of x comma y. So you have x equal to this one. And in order to find the y, you have to plug into the original function. So if you plug into the original function, now if you want to find the value of the function at 0, your function is, you can quickly look at the function. Your function is x cubed over x squared minus 1. So it will be 0 cubed over 0 squared minus 1, which is equal to 0 over negative 1. That is equal to 0. So that means when x equal to 0, y is also 0. So 0 comma 0 is the inflection point. Let's write that down. So 0 comma 0 is the inflection point. That means at 0 comma 0, the concavity of the function changes. Let me demonstrate that using the graph of the function. You can also draw this graph in your note catcher. So let me draw the axis first. Suppose that is my y-axis. Let me draw the x-axis. Suppose this is my x-axis. We also know that the function is undefined at plus 1 and minus 1. So let me also draw those two lines, x equal to plus 1 and x equal to minus 1. So here at x equal to positive 1, okay, here at x equal to positive 1, suppose that is x equal to positive 1, and also at x equal to negative 1, let me draw it on the other side. Here at, that is suppose x equal to negative 1. Okay, at x equal to positive 1 and x equal to negative 1, the function is undefined. Denominator will be 0, meaning of that is we'll have the vertical asymptote over there. You can also verify your graph using the calculator. Now, if you draw the graph using calculator, your graph may look something like this. Over there and over here, it will be something like that. And here in the middle, your graph is like this, like that. So this is the inflection point that we got, which is 0 comma 0. Meaning of that is, when you go from left to right, you can see that over here, the graph is concave up. If you look at the way the graph is drawn, you can see that it's concave up. And after that point, you can see that the graph is concave down. So that is the inflection point. Is the point where the second derivative is 0. It is obtained by checking these two values, where the second derivative is 0 or second derivative is undefined. And also, it is the point where the concavity on the graph changes. Here, the graph is concave up. And here, after that, the graph is concave down. So 0 comma 0 is the only inflection point for the graph of the function. So the graph on the red is the graph of that function f of x equal to x cubed over x squared minus 1. Example, determine the inflection points. So again, we are looking for the inflection points. That is the points where the second derivative is 0 or the second derivative is undefined. So determine the inflection points on the graph of the function. Here is our function f of x equal to e to the negative x squared. That's our function. F of x equal to e to the negative x squared. And I have something about this function over here. This is the function that describes the Gaussian or normal distribution of continuous random variable in statistics. So in statistics, we use this function to model the normal distribution. So that's all about that function. That's the name of that. So once you find the point of inflection, we have the additional thing that we need to find on this in this problem. Also find the interval on which the function is concave up. So if you want to find where the function is concave up, that is where the second derivative is positive. Second derivative is positive, that is concave up. And the interval on which the function is concave down. So if you want to find where the function is concave down, that is the place, or that is the interval where the second derivative is negative. So what I'm going to do first is, I'm going to sketch this function so that you'll have clear idea of how this function might look. So I'm talking about the normal distribution. So it should look like the graph of the normal distribution that you have seen in your statistics class if you have taken one. Okay, suppose that vertical line is my y-axis. This horizontal line is my x-axis, and the graph of the function y equal to e to the negative x squared, it will look like this, a bell-shaped curve. And we call it the graph of normal distribution. So this is the graph of y equal to, or f of x equal to e to the negative x squared. We are asked to find the inflection points first. So in order to find the inflection point, I need the second derivative. So let's try to find the second derivative of this function. So for that, we have to start with our first derivative. Here, my function is f of x equal to e to the negative x squared. So it is not e to the x, instead e to the negative x squared. So your outside function is the exponential function. Your inside function is negative x squared. So we use the chain rule. So if you use the chain rule, the derivative will be, okay, f prime x equal to the derivative of the outside function, exponential function, is e to the whatever is there inside. And then we multiply by the derivative of inside function. Derivative of negative x squared is, by using the power rule, 2 will come in front and we reduce the power by 1. So that will be negative 2x. Negative 2x. So that is my first derivative. First derivative is f of x equal to e to the negative x squared times negative 2x. So the second derivative will be, so if you want to find the second derivative, we have to use the product rule, because this is my first function, e to the negative x squared is first function, multiplied to the second function, which is negative 2x. So let's use the product rule. First function, e to the negative x squared, times the derivative of second. Derivative of negative 2x is negative 2, plus the second function is negative 2x, multiplied by the derivative of e to the negative x squared. We already know the derivative of e to the negative x squared because our original function was e to the negative x squared, and we got the derivative here. This is the derivative. So the derivative of e to the negative x squared will be e to the negative x squared times negative 2x. Now we can simplify this a little bit and we can make it beautiful. let me continue here. This is my first term, that is my second term. In these two terms, we have e to the negative x squared common. So I can factor that e to the negative x squared out. And after factor that out, here I have negative 2x times negative 2x, which is positive 4x squared. And then on the first term, I'm left with minus 2. So I can write the second derivative as second derivative is equal to, I have 4x squared minus 2. And then if I move this e to the negative x squared to the denominator, it will be e to the positive x squared. So that is my second derivative. We need the second derivative to determine the inflection points, because inflection points are the points on the graph of the function where the second derivative is 0 or second derivative is undefined. Now, if you look at this function f of x equal to e to the negative x squared, the graph is also here. You can clearly see that the domain of this function is from negative infinity up to infinity. That means the graph or this function is satisfied by all real numbers. If it is imaginary, it will not take that value, but it will take all the real numbers from negative infinity up to positive infinity. And we have the second derivative equal to 4x squared minus 2 over e to the x squared. In order to find the inflection point, we check where this is 0 and where this is undefined. Now, let's see, f double prime x, that is the second derivative, is 0 when, you can see second derivative is 0, this is a fraction, so it will be 0 when the numerator is 0. That is when 4x squared minus 2 equal to 0. So meaning of that is, let's solve this. Add 2 on both sides, that's what you'll get. Divide on both sides by 4, you get a half. Then you'll get x equal to, if you take the square root, plus or minus 1 over square root of 2. Square root of 2 is approximately 0.7. So if you want to know this as a decimal value, it is approximately 0.7 plus or minus 0.7. Now that is the first case. Second derivative will be 0 when the numerator is 0. And second derivative is undefined. Also, second derivative is undefined when the denominator is 0. E to the x squared equal to 0. But you can see here e to the x squared, whatever number you plug in from negative infinity up to positive infinity, it cannot be 0. So e to the x squared is 0. That is impossible. So there is no way that this will be 0. This is impossible. That means the only candidate for the inflection point is plus or minus 1 over square root of 2. So let's find the value of the function at these two values. Now, if you want to find the value of the function at 1 over square root of 2, our function is this, e to the negative x squared, which is same as 1 over e to the x squared. E to the negative x squared is our function that is given to us, which is same as 1 over e raised to x squared. Now, if you plug in the value, it will be 1 over e raised to, we have to square the x. If we square this one, it will be 1 over 2. And this is equal to 1 over square root of e, because power half is a square root. So when you plug in half, not half, 1 over square root of 2 to the function, your output is 1 over square root of e. Similarly, let's plug in the other value, which is negative 1 over square root of 2. So if you plug in negative 1 over square root of 2, that is 1 over, you are plugging in here, so e raised to negative 1 over square root of 2 squared. When you're squaring it, negative will be positive, and 1 over square root of 2 square of that is half again, which is equal to 1 over square root of e. So meaning of that is The inflection points are the inflection points are plus or minus 1 over square root of 2, and the y value is always the same, 1 over square root of e. So those are the inflection points. So if you want to show them on the graph, these are the points here. Oh, hold on. So this is the point. This is the point, and at this point is the inflection point. Negative 1 over square root of 2 comma 1 over square root of e, and this one here, the other point, is 1 over square root of 2 and 1 over square root of e. Now let's find out where the function is concave up and where it is concave down. So we are going to talk about concavity now. We want to explore the concavity for this function. We know the domain of the function. Domain of the function is from negative infinity up to infinity. And we got the inflection points at x equal to 1 over square root of 2 and negative 1 over square root of 2. So negative 1 over square root of 2, let me label that here, negative 1 over square root of 2 and positive 1 over square root of 2. So those are the two values. And at these two values, okay, at 1 over square root of 2 and negative 1 over square root of 2, the second derivative is 0. So what we already know is here the second derivative is 0. Here the second derivative is 0. The concavity changes over there. Now we need to find out how is concavity in this interval. The value of x, 1 over square root of 2, is approximately 0.7. So this is negative 0.7. That means from this interval, what I can plug in is, I can select one value from this interval. That is negative 1, because this value is negative 0.7. The closest whole number will be negative 1. So I can plug in negative 1. So let's try to plug in negative 1 and check what we get. When x equal to negative 1, the second derivative at negative 1 will be, we are calculating the second derivative, so we plug in here. If I plug in negative 1 squared is 1. 1 times 4 is 4. 4 minus 2 is 2. And then in the denominator, 2 over, if I plug in negative 1 squared is 1. So e to the 1, which is e. 2 divided by e is a positive number. 2 is a positive number. So my second derivative in this interval is positive. Second derivative over here is positive. That means in this interval from negative infinity up to negative 1 over square root of 2, the function is concave up. Now let's check here in the second interval. Between negative 0.7 and positive 0.7, I can select 0. So let's plug in x equal to 0. When x equal to 0, the second derivative at 0 will be, if you plug in 0 here, so 4 times 0 squared minus 2, that is negative 2, over, if you plug in 0, 0 squared is 0, e to the 0 is 1. So that will be negative 2. Second derivative is negative in this interval. Meaning of that is the graph of the function is concave down on this interval. Now let's check here on this interval from 1 over square root of 2, that's from 0.7 up to infinity. I can select 1 as the test value. So let's do that. When x equal to 1, the second derivative at that point will be, okay, if I plug in 1 squared is 1, so 4 times 1 is squared, 4 minus 2 is 2, 2 divided by, in the denominator, if you plug in 1 squared, that's 1, e to the 1 is e. Both are positive, so positive divided by positive is positive. So in that interval, the second derivative is positive, meaning of that is the graph of the function is concave up. So we can write our conclusion. Let's write that. Hence, the graph of f of x is concave up on, so you can see it is concave up in this interval from negative infinity up to negative 1 over 2, negative infinity up to negative 1 over square root of 2, and also from 1 over square root of 2 up to infinity. And if you want to combine these two intervals together, we write union, if you remember from your college algebra or pre-calculus. So these are the two intervals on which the function is concave up, and here in the middle it is concave down. And concave down on the interval from negative 1 over square root of 2 up to 1 over square root of 2. And if you want to verify this with your graph, it works perfectly. You can see from negative infinity up to this value, which is 1 over square root of 2, you can see the graph is concave up. And then from negative 1 over square root of 2 up to positive 1 over square root of 2, you can see the graph is concave down. And after that, the graph is again concave up. So these are the intervals where the graph is concave up, and this is the interval where the graph is concave down. So this is how we can determine the concavity. Example, a rectangle has its base on the x-axis and upper two vertices are on the parabola y equal to 4 minus x squared. What is the largest possible area of the rectangle? So first, we are going to draw the rectangle based on the information given here. So the rectangle has the base on the x-axis and two vertices or two upper vertices are on the parabola y equal to 4 minus x squared. So first, we are going to draw the parabola y equal to 4 minus x squared. Since x squared is negative, it's a downward facing parabola, and the y-intercept is 4. So we draw the parabola facing downward like this. So this is the parabola y equal to 4 minus x squared. Now, let's draw the rectangle. So rectangle is just like this. It has the base on the x-axis. So this is the base on the x-axis and two upper vertices, that is this one and this one. These two vertices are on the parabola y equal to 4 minus x squared. Now, if we consider this point here as x, or at a distance of x from the origin, then by symmetry, this point is negative x. So if this is x comma 0, then this point is negative x comma 0. Then the point on the parabola over here is x coordinate is x, and the y coordinate is obtained by plugging in x in place of x. So y is always 4 minus x squared. So 4 minus x squared. Similarly, this point will be negative x comma 4 minus x squared. Now, by looking at this rectangle, we have the length and width of the rectangle here. The length of the rectangle is this distance, which is, so if you want to find the horizontal distance, it is this x minus that one, x minus or negative x, which is equal to x plus x, 2x. And the width or the height of the rectangle is the y coordinate, the difference in the y coordinate. Here the y coordinate is 4 minus x squared and here is 0. So when we subtract 4 minus x squared minus 0, that is 4 minus x squared. We want to maximize the area. What is the largest possible area of the rectangle? So because we want to maximize the area, our objective function is the area function. So let's write that area. Now the area in terms of x is length multiplied to width. So 2x multiplied to width is 4 minus x squared. So that is equal to, let's simplify this, 2x multiplied to negative x squared is negative 2x cubed negative 2x cubed, then plus 2 times 4 is 8x. So that is the area function. Now we want to find, or we want to maximize this function. We know that the maximum or minimum value occurs at the critical point. That is where the first derivative is 0 or undefined. And also I'm going to use the second derivative test to verify whether the function has the maximum or minimum value at the critical point. So let's first find the first and the second derivative. So this implies the first derivative is equal to, if we find the first derivative, 3 times 2, 6, so negative 6x squared, then plus 8. And the second derivative is, second derivative, a double prime x, that will be equal to, we have to find the derivative of the first derivative to get the second derivative. Derivative of 8 is 0. Derivative of negative 6x squared is 12x, negative 12x. Negative 12x. So we can easily find the critical point by setting the first derivative equal to 0. So if the first derivative, if negative 6x squared plus 8, first derivative is equal to 0, then by solving this equation, we have x equal to plus or minus 2 over square root of 3. So that is the value of x by solving this equation. So these two values are the candidate for the maximum or minimum value. That means the maximum or minimum value may occur at these two critical values. Now, in order to check whether we have maximum or minimum value at this point, we need to plug in to the second derivative. So what we are going to do is we are going to plug in these values to the second derivative. We are only looking for the largest possible area. That is, we are looking for the maximum area. So the second derivative at, let's plug in the positive value. Positive value is 2 over square root of 3. 2 over square root of 3 to the second derivative. And second derivative is negative 12 times x. X is 2 over square root of 3. So if we simplify this, this is equal to 24 over square root of 3. So we get the second derivative as negative. So since the second derivative is negative, the function, that is the area, is maximum when x equal to 2 over square root of 3. We want the largest area, so we got that. It is when x equal to 2 over square root of 3. So we can write area is maximum when x equal to 2 over square root of 3. That is when the area is maximum. But our question is, what is that largest possible area? So what is that maximum area? We need to find that maximum area. We already have the area function. Area as a function, area is equal to 2x times 4 minus x squared. So if we plug in here, we'll get the area. So we write, hence the maximum area, hence maximum area is equal to length multiplied with width. Length is 2x, so 2 times that. 2 times 2 over square root of 3. And then multiplied to the width is 4 minus x squared. So 4 minus x squared, square of this x. When you square this, it will be 4 over 3. 4 over 3. Which is equal to 2 times 2, 4 over square root of 3. 4 over square root of 3 multiplied to, now we need to multiply this one with this value. So let's simplify this one. 4 minus 4 third, it will be 8 third. 4 minus 4 third is 8 third, because if you try to make the common denominator here, we have 3 in the denominator and we multiply the numerator by 3. So 3 times 4, 12. 12 minus 4 is 8. So that will be 8 over 3. 8 over 3. So that is equal to 8 times 4, 32 over 3 square root of 3. So that is the maximum area. If we change this to decimal, if we simplify using calculator, So it is 6.1584. So that is the maximum possible area of the rectangle whose base is on the x-axis and two upper points are on the parabola y equal to 4 minus x squared. Example, find a point on the graph of the function y equal to square root of x that is closest to the point 2 comma 0. So first, let's draw the graph of the function y equal to square root of x. That's my x-axis, that's y-axis. So the graph of the square root function is like this, which is y equal to square root of x. The general point on the graph of this function is x comma square root of x, because y is always the square root of x and the general point is x comma y. So x comma square root of x. We have to find what point on this graph. So I'm just writing the general point here. So we have to find the value of x comma square root of x, so that this distance between the point 2 comma 0 and any point on that curve, the general point in this case, but when you find the closest point, it will be minimum. It has to be minimum point. And what is that point? So for this distance, in other words, for this distance, okay, for the distance d to be minimum, we have to find the value of x comma square root of x. So let's use the distance formula to find this distance. Here, the distance d is equal to square root of, when you find the distance, we use the distance formula, that is difference in x coordinate squared, which is x minus 2 squared, plus difference in y coordinate, which is square root of x minus 0, square root of x minus 0 squared. So that is the distance formula. If we square this, we write d squared equal to, okay, when we square this, the square root will be cancelled. And here we have x minus 2 squared, that is x minus 2 times x minus 2. If we FOIL that, it is x squared minus 4x plus 4, then plus square root of x minus 0, square root of x. When you square it, it is just x. So let me consider that d squared as uppercase d of x. So I'm replacing d squared by d of x and simplifying the right hand side, x squared minus 3x plus 4. So this distance will be minimum if this d of x is minimum. So that is something we need to note. D is minimum when d of x is minimum. So meaning of that is this function is my objective function. So I need to minimize this. So in order to maximize or minimize the function, we already know that the maximum or minimum value occurs at the critical point. That's the point where the first derivative is equal to 0. And I'm going to use the second derivative test to verify whether the function has the maximum or minimum value at critical points. So we are going to find the first and the second derivative. So this implies the first derivative is equal to the derivative of x squared minus 3x plus 4 is 2x minus 3. And the second derivative, if you find the second derivative, it will be d double prime x is equal to second derivative, that is the derivative of 2x minus 3 is 2. Now in this case, the second derivative is positive. So whatever we get from the critical point, the second derivative is positive. Meaning of that is this function is always maximum. So we can write here, since second derivative is always positive, d of x will be minimum at critical points. So now in order to find the critical point, we set the first derivative to 0. So let's do that. if the first derivative is 0, first derivative is 2x minus 3 equal to 0, then x equal to 3 over 2. Meaning of that is the distance is minimum when x equal to 3 over 2. So let me write the meaning of that. Meaning d, or the distance, is minimum when x equal to 3 over 2. But our question is, we have to find the point. Point is x comma square root of x. So the required point on the graph for which the distance is minimum is x, which is 3 over 2, comma square root of 3 over 2. So the required point, is 3 over 2, comma square root of 3 over 2. Example, find the maximum and minimum value of the function f of x equal to 3x over x squared plus 1 on the interval from -2 up to 2. So here we have a function given. The domain of the function is from infinity up to infinity, but we are interested only in this interval from -2 up to 2. Now, we need to find the maximum or minimum value. We know that the maximum or minimum value occurs at the critical point. That is the point where the first derivative is undefined or first derivative is 0. And also, in order to verify whether we have maximum or minimum at the critical points, we are going to use the second derivative. That means we need to find the first and second derivative of this function first. So let's find the first and the second derivative. Here, the function is 3x over x squared plus 1. So this implies the first derivative is equal to, okay, let's use the quotient rule to find this derivative. It's denominator, which is x squared plus 1, multiplied with the derivative of numerator. Derivative of 3x is 3, minus numerator 3x, multiplied with the derivative of denominator. Derivative of x squared plus 1 is 2x, divided by the square of the denominator, so x squared plus 1 quantity squared, which implies the first derivative is equal to, after simplifying this expression, we get 3 minus 3x squared divided by x squared plus 1 quantity squared. So that is the first derivative of the function. Now we are going to find the second derivative. That is, we are going to differentiate this one more time to get the second derivative. So the second derivative is equal to, again, it is in the form of a quotient. So we are going to use the quotient rule. Quotient rule says denominator, which is x squared plus 1 quantity squared, multiplied with the derivative of numerator. Derivative of 3 minus 3x squared is negative 6x. Negative 6x. Minus the numerator, which is 3 minus 3x squared, multiplied with the derivative of denominator. In order to find the derivative of the denominator, we use the chain rule. First, we find the derivative of outside function by using the power rule. That will be 2 times x squared plus 1. And we multiply by the derivative of inside function, which is 2x. And we divide everything by the square of the denominator. We have x squared plus 1 quantity squared in the denominator. When we square this, it will be raised to power 4. Okay, after simplifying this, the second derivative will be 6x cubed minus 18x over x squared plus 1 raised to 3. Make sure you simplify this and verify the second derivative is this one. Now, we need to look at the critical points. These are the points when the first derivative is 0 or undefined. In this case, the first derivative is always well defined because your denominator is always a positive number. So the only possibility is the first derivative can be 0. So when this first derivative is 0, then we get x equal to plus or minus 1. So these are the critical points. These are the values at which the function has the maximum or minimum value. The function will be maximum when the second derivative is negative, and function will be minimum when the second derivative is positive. So we are going to put these values into this function to see whether we have maximum or minimum value. So when x equal to positive 1, the value of the second derivative at 1 is equal to, okay, if you plug in 1, it will be 6 times 1 cubed minus 18 times 1. So that will be 6 minus 18, which is equal to, if we subtract 6 minus 18, that will be negative 12. Negative 12 over, in the denominator, 1 squared is 1, 1 plus 1, 2, 2 cubed is 8. So we get a negative value. Meaning of that is the function is maximum when x equal to 1. So this implies function is maximum when x equal to 1. So at 1, the function is maximum. Similarly, when x equal to, now let's plug in negative 1. If you plug in negative 1, the second derivative will be by plugging in negative 1. If we plug in negative 1, this will be negative 6, that will be positive 18. So 18 minus 6, that will be 12, and denominator is positive 8 again. So 12 over 8. So we get positive value, meaning of that is the function is minimum when x equal to negative 1. So we can say the function is minimum when x equal to negative 1. Now, if you look at the question, we are asked to find the maximum or the minimum value. So that means if we plug in x equal to 1, we get the maximum value. And when you plug in negative 1 to the function, we get the minimum value. So we can write this. So function value is maximum at 1. We have seen that. So plug in 1. So it will be f1. The maximum value of the function is f1. So if you plug in 1 to the function, 3 times 1 is 3, and then 1 is squared plus 1, that is 2. So we can write 3 times 1 over 1 is squared plus 1, which is equal to 3 over 2. So 3 over 2 is the maximum value. Similarly, the minimum value will be, it will be obtained by plugging in negative 1. So if you plug in negative 1, it will be 3 times negative 1 over negative 1 is squared plus 1. 3 times negative 1 is negative 3 over negative 1 is squared is 1. 1 plus 1, that is 2. So the maximum value of the function is 3 over 2, and the minimum value is negative 3 over 2. We can easily verify this by drawing the graph of the function. So if we want to draw the graph of this function, let's try to sketch the graph here quickly. That's my x-axis. This is my y-axis. If you try to sketch the graph of the function using your calculator, you'll see that your graph increases like this here and decreases like that. This side, it's going down and then up like that. So that is the graph of the function. Now, if you try to find, or if you try to look at this graph carefully, you can see that it's increasing here, it becomes maximum there and decreasing. This side it is decreasing, minimum there, and this side it's again up. So the minimum value is here. If you try to verify with your calculator, that point is negative 1, comma, negative 3 over 2. That is at negative 1, you can see at negative 1, it is negative 3 over 2, and that is the minimum value. And then this one is the maximum value. If you try to check this point using your calculator, it is 1, comma 3 over 2, and that is the maximum value. We saw that maximum value occurs at 1, and the maximum value is 3 over 2. So that is the end of this lecture. Thank you so much for watching. I hope you find this helpful.